So what are we covering today?
Okay. I have my test review for tomorrow.
Okay. Are you covering
And
surface areas and volumes of solids?
no, I'm doing piecewise and let's see here. Rational functions
Okay.
and transformations.
Sounds like stuff you can verbalize.
Yeah.
Okay.
All right. Let's see. Okay, so for the piecewise, should I just give you the equation first or the...
Yeah, start from the top left.
Okay, so 1/2 x squared plus 2x minus 1, and then it's x has to be less than -4.
Okay.
And then 2 square root 5 minus 5x. And then -4 is less than or equal to x, which is less than 0.
And I'm guessing there's one more.
There's 2 more.
Oh, I shouldn't write that then.
And then 2 to the x, and then 0 is less than x, which is less than or greater to 4.
Looks like we've got at 0, we got a less than 0 and a greater than 0. Is one of those greater than or equal to?
No, it says...
So x is not defined at 0?
Right.
Okay.
And then it's an absolute value, and then within the absolute value is 3 minus x. And then x has to be greater than 4.
All right. What I usually tell people to handle piecewise functions is to start with your domain in the upper right.
Okay.
Okay. Now, we have so many of them here that I'm not sure I can fit everything on the page. Let's see. Now, let me start this way here. I want to plot this function everywhere where x is less than -4. In other words, in this entire space from -infinity to 4, I'm going to plot this function. Okay? And I'm going to go through that. In other words, from -4 to 0, I'm going to plot this second function. From 0 to 4, I'm going to plot the third function. And from x greater than 4, I'm going to plot the fourth function. Okay? So we have a fair idea at what those functions look like. The first one is clearly a parabola. What is that? Is that 1/2 x times x? Let's see. Let me think for a moment as to how I want to best explain this. If I were to plot that parabola in totality, maybe it would look something like that.
Like the parent function?
Now look what I drew. Yeah. In other words, that's a flat parabola.
Yeah.
Flatter than normal because the coefficient of 1/2. Faces upwards. If that was the only function for all x, I would plot it with this red parabola down here. Okay? And one way to think about this is plot everything and then erase the part that doesn't belong in our domain. In other words, it would stop right there, like that.
Right.
Okay? Well, now, what is that point right there? Is all we really need to plot this is that point. We don't need to know how to plot the entire parabola. We need to know what that point is. Well, what is f of minus 4?
So -4 squared is going to be 16, and then half of that is 8, and then plus 8. Minus 1.
8.
Minus 8, yeah.
Minus 1. So this parabola actually comes in right there.
Okay.
Okay. So and I know that it's going to look like this, right? I mean, maybe if I were to plot the whole thing, it might end up doing something like that, but it's not for the whole area. It's only for this part of the domain. And should that be a closed circle or an open circle?
Open.
We know it's an upward-facing parabola, so that's probably good enough. If we need more points on that curve, we can plot more points. I can go out and put in x of minus 6 and see where we're at so that I have 2 points at least to plot that. Okay?
So,
but that's not what's really important. Getting the exact curve isn't what's important. It's handling the transition from domain to domain. Okay? So, now let's go to the second region.
But the only point that you need to know is just the one, like -4, that's the only point.
Yeah, you'll see when I'm done why that's the most important point. I mean, obviously, if you were trying to plot the perfect graph, we'd probably want to know where the x-intercept is and maybe one more point. You really need 3 points to plot a parabola.
Yeah.
And that's all you need. But for the purposes of this problem, the only thing we really need to know is where it crosses this line, x equal minus 4. Okay? After we're done with this problem, I think you'll understand why I don't care too much about what these other points are. So the next area that we're going to plot in is going to be in this region. Okay? And that looks like, well, it's a square root function. Looks like it might be a square root function that, well, let's figure out where the square root function starts and where it ends.
Doesn't it start at 0, 0?
No, it starts right there.
Oh, sorry, I thought you meant like the parent function of it.
Yeah, let's always work from left to right.
Okay.
So to figure out where it's going to cross this this imaginary line that I've put in here, this dotted line, let's plug in minus 4. Well, what does that give me? The square root of 25 times 2, 10. So it crosses up here at 10. Now let me label that on the other side so I've got room. It's greater than or equal to, so it's closed dot. And then where does it cross the y-axis? Because this is the next key point.
So it's square root of 5 times 2?
Correct. Square root of 5 is a little bit more than 2. So times 2, we're looking at a number, it's about 4.
Mm-hmm.
We'll call that 2 root 5. And it's an open dot right there. And what does this function look like? Well, let's talk about what's the square root function look like. Looks like that, right?
Mm-hmm.
In other words, this is y equals square root of x. Well, what would y equals square root of negative x look like? It would be a reflection over the y-axis.
Mm-hmm.
So it would look like this.
Okay.
Okay, and that's what's going on in this region, is we have a negative sign in front of the x.
Mm-hmm.
So it's going to look like this.
Okay.
Okay?
Mm-hmm.
That's the second region. Again, we don't care so much if we have all, I know that point is correct, and I know that point is correct, and I know what the general shape of the curve should look like. So that's got to be pretty accurate. Okay, the next region is from 0 to 4. I'll put a dotted line there just so we know the region we're talking about.
Mm-hmm.
This is the next region I want to draw a function in. Let's move that 2 square root of 5 to the other side just so it doesn't get in the way. Okay, and in this region here, we're looking at the exponential function. Well, I know what that exponential function looks like. What is it at 0? In other words, the first point, the first point we want to examine is that 0 right there.
Mm-hmm.
So 2 to the 0th power is 1, which is like right there. Open or closed dot?
Closed. Open.
Open, and that's why I question it, because you rarely have open.
Yeah.
In other words, that makes this function have a hole, basically, at 0. In other words, this is saying that x cannot be 0. But that's okay. We know what exponential functions look like. What does 2 to the 4th equal?
2, 8 through 32.
I think 16.
Oh.
2 times 2 times 2 is 8, times another 2 is 16.
Okay.
Okay. So, and anywhere greater than, anywhere greater than, so it's a closed dot at 16 because of that.
Yeah.
It's an open dot at 1 because of that. And I know what an exponential function looks like. It looks like that. So this thing is going to look like that.
Okay.
Okay. And now the only interval left is this greater than 4. Well, what does the absolute value function look like? Greater than 4. A typical absolute value function looks like this. Okay. So we know it's always going to have a v in it. There's no negative sign in front of the absolute value, so it's not going to be turned upside down. And the negative sign that's inside does tend to reflect it across the y-axis, but in this case, that makes it look pretty much the same.
Yeah.
In other words, where is at x equals 4, we're at 1. Right there. At x equals 5, we're moving up. As x gets bigger, we move up like that.
Mm-hmm.
At x equals 1,000,000, we're at 999,997.
Mm-hmm.
Okay? In other words, the way this function would look if we carried it all the way back, it would be, there's our corner. Well, we're not going to see that part because that's not the part in our domain. In other words, we're looking at nothing but positives here because it's only when x is greater than 4. And when x is greater than 4, the absolute value of -1 is 1.
Mm-hmm.
When x is 5, the absolute value of -2 is 2. So as x moves to the right, this moves straight up. It effectively looks linear with a slope of 1. Okay? And now we have everything. And you can kind of see why it's not terribly important to have all the points proper on this first part of the piecewise function.
Right.
The important part is that we're showing 4 different looking functions and that we have our crossover points correct. In other words, is that correct? 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 And is that correct? That's the most important thing when you're graphing piecewise functions. Okay? And this is definitely one of the stranger ones I've ever seen because, well, it combines 4 different elementary functions. This is a quadratic, this is a square root function, this is an exponential function, and an absolute value function. So all of these tend to have their own peculiar shapes. And the only one that we might have had difficulty with was the second one. But notice by plotting that point and knowing just a little bit about how the square root function looks, allowed us to fill in the rest of it.
Right.
One thing you definitely need to know is what these basic functions look like. There's 12 elementary functions. You need to know that quadratics are parabolas, square root functions, what they look like, what exponential functions look like, and what absolute value functions look like. Now, this is a little bit of a fooler because you expect an absolute value function to look like that, and the only part we see is just a straight line. That's because the vertex would have come back here where it's not defined.
Right.
All right. We finished that problem? I think we did. I don't know anything else to say about it. And of course, well, one thing is we do need arrows there.
Right. Some of the other ones that she gives us at the very end when you're done graphing, it says evaluate, and then she'll give like
go ahead.
F is -2, but this one doesn't have any specific ones, but I have different
that's
ones.
Pretty easy. If we said what is F of -2, what would it be?
It would have to be in the second function.
Correct.
So would you just plug -2 in there?
Correct.
Okay, so 10, that would be 2 square root 5, right?
2 square root of 15, notice.
15, oh, because it's negative, okay.
Right, in other words, when I plug in -2, I got a 5 minus 10, which is the same as 5 plus 10, so this becomes 2 root 15.
Okay.
Okay? And so no matter what number she gives you, if she gives you F of +2, you're going to plug it into that one.
Right.
In other words, you search over here. What I tend to tell people when we're talking about piecewise functions is I like starting up there conceptually, upper right. Because that starts at -infinity and goes to whatever that number is. And we want to graph this thing from left to right. So considering the domain, the first domain region we want to go from is -infinity to -4.
Okay.
And then continue and do that one next, and then that one, and then that one.
Okay.
And I like that way of analyzing piecewise, regardless of which way you're going. In other words, they're going to ask you to go both ways on this. They're going to give you the piecewise function and ask you to graph it. And they're also going to show you a graph of a piecewise function and ask you to figure out what the functions are.
Yeah, I have some of those.
Those are going to be tough to do with verbal.
Yeah.
If you have one of those that you really want to do, take a quick picture of it and send it to me, and then I can pull it up on my screen.
All right, I'll do that.
Okay. Those are a little harder to do. Notice that if I was trying to do this backwards, I might have difficulty figuring out what that function is right there.
Yeah.
Figuring out that it's 2 times root 5 minus 5x, gosh, I don't know if I'm going to be able to figure out how to do that or not, but they generally make the functions a little easier to figure out.
Yeah.
If they give you a picture of it. This is about the most complicated one I've ever seen, actually. Especially given the whole at 0. You don't usually the domain is all reals.
Yeah.
So that they don't put any areas on there that x can't be. But according to this definition over here, x can never be 0.
Right.
That's why we have a hole there and there.
Yeah.
Okay. Must have been your email. Did you send it?
Yeah, I sent it to your...
Send it to David Cowan 1949 at Gmail?
Hold on.
You send it to David at Digital Math Tutor.
I might have done that.
That one gets forwarded to me. Sometimes that one can take like an hour to get to me. So the best one to send stuff to is David Cowan 1949 at gmail.com.
Alrighty.
Try resending it if you sent it to the other.
Yeah, I'll send it.
Okay. And I can write that out and spell it for you if you need it. Right there.
Okay.
Yeah, I don't remember you sending me a whole lot of stuff. So this might be the first time you've sent me something. So you might have to type it all out. Once you type it out once, the next time you just generally have to type out the first 2 letters.
Yeah. Okay, it said it's sent.
Okay, yeah, I see it. Are you on an iPhone or a Samsung?
iPhone.
Okay. Only thing is you have to make, it looks like you did, sent it as a large picture, yeah. Because they give you that choice to send it small or send it big.
Yeah.
Okay. Is number 6 the only thing we want to look at here?
Yeah, I think that's the one I'm confused on.
And notice that we're not going to have any difficulty figuring out what these functions are.
Yeah.
That's clearly half of a parabola that's upside down.
Mm-hmm.
That looks like a step function between there and there, the greatest integer function.
Yeah.
And in fact, between there and there, we have the greatest integer function, and then we just have a straight linear function from there to there.
Yeah.
Okay, so let's see if we can figure out what each of these functions are.
Okay. If the absolute value functions look exactly like the linear functions, how do you tell the difference between them if they give you a graph?
Very good question. And I'm not sure what the answer is. I think the answer is that there's not just one unique solution here.
Yeah, there's something else you can get.
I could define this part of the graph as either a linear or an absolute value function. Just like the last one, I could have done that.
Okay.
In other words, this, if we look at that last one, notice that this could have been defined just linear with a positive slope.
Yeah.
And I wouldn't have been able to tell the difference between that and the fact that it actually was the absolute value of 3 minus x.
Right.
Linear, that looks like it would be y equal x minus 3. In other words, that line that I've drawn there is y equal x minus 3. It's also the absolute value of 3 minus x.
Okay.
So there may not be a unique solution when I'm going the other way.
Right.
Doesn't really matter, but let's start from the far left.
Okay.
Okay. So x is what? We're going to start defining our piecewise function in the upper right.
Okay. So with, because couldn't that be a square root function too? Or no?
Maybe, I don't know. Well, we'll plug in these 2 points. It doesn't look like a square root function because the square root function looks like this. In other words, it has a starting and stopping point right there.
Okay.
And this kind of indicates that it goes all the way. I suppose no, I can't even imagine how you could translate that square root function to end up looking like this. Wouldn't have a 0 there anyway.
Right.
So I don't think it's the square root function. It looks to me like it's just an upside down parabola. Okay. But first things first, let's define the domain.
Okay. So it has to be less than 4, but greater.
Now, we're talking about this part, this function right here.
Yeah.
That function applies whenever x is less than 0.
0. Oh, sorry. I was looking at the y value.
Okay. Remember that when we're talking the right part of these piecemeal functions, we're always talking x. We're only talking domain.
Right.
It's less than 0 because that's an open dot right there.
Right.
Okay. Now, let's go ahead and figure out what that function is.
Okay.
It looks to be something like this. Right?
Right.
In other words, y equal minus x squared would look like that. Y equal minus x squared plus 4 would look like that.
Right.
Now, the question is that the function? Well, when y is 0, it looks like x should be minus 3, so no, that's not the function.
Right.
So let's do this the proper way. Y equals a times x minus h squared plus k. That's a parabola. Okay? Can we solve? In other words, we need to come up with we need to know what a, h, and k are.
Okay.
Well, h and k are pretty easy. What are h and k? Or it's that's the vertex format for a parabola.
Right.
Okay. H and k being the vertex.
Yeah.
So what's h?
So h would be plus 3, wouldn't it be?
H is the x-coordinate of the vertex.
X coordinate. Oh, 0. Oh, okay. And then 4. Okay.
Okay, so now we know this much. Y equals a times x squared plus 4. So now is all we need to do is solve for a. Well, they've given us a point right there. See it?
Mm-hmm.
When x is minus 2, y is plus 2. So if I take this formula here and plug in the y value and the x value, I'm going to be able to solve for a.
Mm-hmm.
Well, let's see. I said y was 2 when x is minus 2. What's that give us? 2 equals 4a plus 4. 4a equals minus 2. A equals minus 1/2. So, I know what a is. A is minus 1/2, and what I have circled there is the function that we see. And if you're not positive of that, put in 0 for x, we're right there.
Mm-hmm.
Put in minus 3 for x, only that doesn't cross exactly at minus 3. It's like minus 2 point something. But put in that point, 2 for x. And you end up getting positive 2 for y.
Okay.
Okay. So this function here satisfies that point, and I could test it with that point if I still wasn't certain, but I guarantee it's going to work for that point also, which tells me that that is absolutely a parabola, which is in vertex format. Here's our answer. Okay. So I go back up. So f of x is equal to minus 1/2 x squared plus 4, whenever x is less than 0.
Okay. If they give you 2 points, can you do the slope by like y2 minus y1 and then x2 minus x1? You can do that?
So yeah, you don't really need to. In other words, when we get to this part here, this is just straight linear. It's all we need is the slope, right? In other words, we know the definition of that part of the line is going to be y equal mx plus b.
Okay.
Okay. Well, let's jump to that since we're talking about it, and then we'll take care of this middle part in the middle.
Okay.
So I'm going to jump to the third part here, which is whenever x is what?
X is greater or equal to 3.
Correct. Okay, so we're talking about what is the, we know the general formula for a linear function is y equal mx plus b. What's the slope?
So you would take...
Just measure it. The ride over the run.
So 2 over 1.
So we know this much now. We can't see where it would cross the y-axis, but we have a bunch of points we can plug in to solve for things. Well, I can certainly solve for b by plugging in that point right there. In other words, when x is 4, y is 3. So I'm going to put 3 for y, I'm going to put 4 for x. That's going to let me solve for b. b is minus 5. And now I can go back, substitute minus 5 for that. There is the equation of that line. Okay. So we're going to go up here and we're going to put in it's equal to 2x minus 5 whenever x is greater than or equal to 3. And that leaves just the middle section. Well, that's the greatest integer function. Greatest integer function being this. Meaning if x is 5.1, y is 5. If x is 5.9, y is 5. If x is 6.0, y is 6.
Okay.
Okay? Greatest integer function plots like this. And one function that's really a good real-time function that is the greatest integer function is what grade you're in when you're in first grade. Notice that everybody that is from 6 to 7 years old is in first grade. When you're from 7 to 8 years old, you're in second grade. When you're from 8 to 9 years old, you're in third grade. That is exactly what this greatest integer function acts like. Okay. Now, how is this different than what I've plotted here?
It's down 1.
Correct. So if I add a minus 1 like that, then I'm looking at what we're looking at here. Okay. Now, so in the middle, I know it's greatest integer function, and once again, that's not the only way to get it. I could also add something inside the greatest integer function to get it. But this is one solution. Okay. And what are our parameters here?
X has to be greater than 0?
Well, let's see what's going on at 0. I'd say greater than or equal to. We got a closed dot right there. Okay. And less than what?
3.
Correct. And this is not less than or equal to. There's a closed dot there. But that closed dot is because this part of the function. Okay. In other words, if I've got the greatest integer function from 0 to 3, that's an open dot. Okay. But when you have an open dot underneath a closed dot, is all you see is the closed dot.
Right. Okay. So you can't have two closed dots on top of each other?
Well, not with the greatest integer function, you can't. Okay. The greatest integer function goes closed dot to open dot. Sometimes it goes open dot to closed dot. If I put a negative sign in there, then I'm going to reflect that over the y-axis, and it's going to go open dot to closed dot. Okay? But that's not what we're looking at. We're looking at closed dot to open dot, closed dot to open dot, closed dot to open dot, closed dot up. Okay. That should be your answer. Now, like I said, this actually also happens to be, I could have said that that's the greatest integer function shifted right by 1 unit, which is also that. So either that or that are the same thing in this case. Okay. Both these functions represent what we're looking at that's going on between 0 and 3 on the x-axis. Okay. So like I said, there's not only one solution on these. I could have also written this differently. I could have written this as an absolute value function, whose vertex would have been right there. Okay. Okay. So, but so any solution that fits the picture should be allowed by the teacher. In other words, even though she may have done this problem and come up with greatest integer of x minus 1 inside the brackets, she should not count this wrong because this is the same thing. Okay. All right. And you're going to find almost in all cases here that you're going to see recognizable functions.
Yeah.
In other words, that's a parabola, an upside down parabola. You could maybe make an argument that that's some sort of a square root function that's been reflected twice or something. But don't go out of your way to do that. That's a parabola. This is a parabola here. That's linear.
Okay.
Okay. The most complicated one here is this greatest integer part right there in the middle.
Yeah.
But seeing a parabola and figuring out the equation of it are not quite the same thing. As you can see that this was relatively tough to figure out the equation of that parabola.
Right.
We had to use multiple points. We had to use that point right there and that point right there.
Right.
Okay. Do you need to do any of the others that are on this page? In other words, do you want to do 7?
No, I think I got those.
Okay.
I'm having trouble with rational functions, and we're supposed to find horizontal asymptotes, holes, vertical asymptotes, and then domain and range.
Okay. These just are step by step. Give me the first one.
Yeah. Okay, so 2x to the third minus 1024 all over x to the third minus 64x. And that's it.
Okay. Let's talk about vertical and horizontal asymptotes.
Yeah, she gave us like a kind of a step-by-step sheet. I don't know.
Before we do that, let's do a little factoring up here.
Yeah, right.
Okay. I can factor out I can do a lot of factoring, but the biggest thing I can do is factor out a 2, leaving behind this. That happens to be the difference of perfect cubes. So I can factor that more, but down in the bottom I can factor out an x, leaving x squared minus 64, difference of perfect squares.
Right.
So now let's write it differently. Let me write it 2 times x cubed minus 512 all over, and that x squared minus 64 is x minus 8 times x plus 8.
Right.
So we're I need to factor the top also.
Yeah.
How the top factors?
X minus 8, and then times x squared.
Always opposite sign.
Right. Plus 8x?
It's 8a times b. So yeah, 8x plus 64. And incidentally, that never is factorable.
Right.
Once you've factored difference of cubes or sum of cubes, the quadratic you get, don't spend any time at all trying to factor.
Right.
It won't ever factor. Okay. Now, what's the next step?
The whole is where whichever cancels.
Yeah.
So it would be at 8.
Normally the next step would be figure out your vertical asymptotes from the denominator. So it looks like immediately I would have vertical asymptotes at 0, 8, and negative 8. But You don't. Whenever you have a factor that cancels like that, it's not a vertical asymptote anymore, it's a hole.
Right.
So, let's draw my graph. Now I only have two vertical asymptotes. There's one of them at x equals 0. And the other one is at x equal minus 8. And I have a hole at x equal positive 8. Wherever this graph ends up, I'm going to have a hole there.
Right.
Do I have any horizontal asymptotes?
So she said to look at the degrees. So
Correct. The degree is the same in the top as it is in the bottom.
okay, so that means it's the top coefficient, like the leading coefficient, over the bottom.
The ratio of the coefficients.
Yeah.
The ratio of the coefficients is 2 over 1.
And then plus or minus a vertical shift, but there isn't any.
Yeah, is the only thing you really know. Okay. The horizontal asymptote, if your highest degree polynomial is the same in top and bottom, nothing else matters. Doesn't this minus 1024, this minus 64x aren't even in consideration. Only thing I'm looking at is that. The horizontal asymptote is the ratio of those coefficients because they're the same. If the bottom was bigger than the top, the horizontal asymptote would be at x equals 0. If the top is bigger than the bottom, we have to do the division before we even do anything else. Okay, in other words, if this was to the fourth and this was to the third, first of all, I divide this into that, and I deal with my remainder. Okay. So, let's see. How are we going to graph this thing? Let's put in our horizontal asymptote. Almost left that out. These things almost always tend to be hyperbolic in nature. You know what I mean by that? No. Okay, let's look at the elementary hyperbolic function 1 over x. Has a vertical asymptote at x equals 0 and y equals 0, and it looks like this, with the function being asymptotic with both asymptotes. Okay. So when I say it's going to look hyperbolic, it means that after I've drawn my asymptotes on there, that's my grid pretty much. Right. As to how I'm going to graph it. In other words, most likely, I'm just going to guess for now, just to give you an idea, most likely it's going to look something like this. And then it does something in between these two vertical asymptotes. And I have to figure out whether that in between is like that, or in other cases it will go up and it will turn around like that. Right. Okay, so there's a couple of things we need to determine as to what's going on here. And it isn't always in this quadrant and this quadrant. Right. It sometimes can be in this quadrant and this quadrant. Yeah. So there's a couple of things we're going to need to know before we can figure out how to graph this. Right. And first of all, are there any x-intercepts? In other words, I know there's no x-intercepts from that part. There might be one in that part there. But the key one is whether it's going to cross the x-axis in between those things. Okay. So, to see whether or not there's x-intercepts, I want to set this thing equal to 0. Right? In other words, the x-intercepts occur when f of x is 0.
Okay.
Always remember that. X-intercepts are where y is 0. Y-intercepts are where x is 0. So if I want to set this thing equal to 0, the only thing that matters is the numerator has to be 0, right? In other words, I don't really care what the denominator is. If that whole thing is 0, I need my numerator to be 0.
Right.
Well, there is one place where that's equal to 0. In other words, where this thing here is equal to 0. Where is x cubed minus 512 equal to 0 occurs only at x equals 8. Okay, so I can go to my curve. My curve has to cross that point right there. So immediately that tells me that my thing that I drew as for starters isn't right. Must be this quadrant here. Okay, so I got, and there's a hole. Where's the hole here? Oh, at x equal 8. So not only is that my 0, x cannot be equal to 8, but that's where it would have crossed the x-axis if it could have been.
Okay.
So I've got that whole part done. I also know that it does not cross the x-axis anywhere between 0 and negative 8, or to the left of negative 8.
Okay.
Now, it might be useful to know whether it crosses my horizontal asymptote. Well, for that to be true, this thing would have to be 2. Right? In other words, the y value would have to be 2. If at any point the curve, whatever's in between these two asymptotes here, if it crosses, and it is allowed to cross horizontal asymptotes. You can't cross vertical asymptotes, but you can cross horizontal asymptotes.
Right.
Okay, so it might be, I know it doesn't cross the x-axis. We didn't find any zeros there. Right. It might cross here, so it'd be worthwhile knowing if there's a point in there where it's equal to 2. So now I have to solve that equation.
Okay.
You think for a moment. Well, what I really need to solve is this equation. It's a little simpler. I can divide both sides by 2. So now it has to be equal to 1. So what that means is that has to be equal to that times that. That's the way you get 1. When you divide something by something that's the same amount, you get 1. Okay? So I can say x squared plus 8x plus 64 has to equal x squared plus 8x, which is the product of the bottom.
Okay.
Now, that crosses, that crosses, that crosses, that crosses, and I got an impossible answer. 64 is not equal to 0, which means there is no point in the domain on the x-axis where this function crosses that horizontal asymptote.
Okay.
Okay. So,
she was talking about figuring out if the hole was covered or not, and I'm a little confused on that.
No, the hole is a restriction on the domain. In other words, the moment we crossed out that x minus 8 with that x minus 8, we left the hole. It didn't, just because we crossed it out, didn't remove it. it still means that x is not allowed to be 8.
Okay.
No matter how
So
you
it's not
manipulate
covered?
this function, no, it's not covered. Holes, I'm
Okay.
not sure what she meant by a covered hole. Never heard of a covered.
She
Unless it's a
has
different
a...
point or something like that. But the hole wouldn't be covered. It would just be that at x equals 8, it's a different value. In other words, it would be like a piecewise function.
Okay.
Okay. But I'm not sure what she means by a covered hole like that.
I think, well, she has us like go on our calculator and then I think type in
Your calculator is never going to show that hole, incidentally.
Yeah.
Because it's infinitesimally small.
Yeah.
In other words, it's not even a millimeter in size. It's not even a billimeter.
Yeah.
It's one number only, 8, which is one of an infinite number of points on the x-axis. So it's so small that it's not going to show up, and so we draw a big hole in there just to alert us to the fact that x is not allowed to be 8.
Right.
Okay. Now, there's a couple of things. If we're looking at this curve from right to left, the next thing to figure out is what's going on in the middle.
Okay.
Well, not positive about this, but usually if this ends up going down to negative infinity, which it is, then it comes out the other side of the asymptote with coming from positive infinity.
Okay.
And that's about all that that thing can do. We know it doesn't cross the x-axis. We know it doesn't cross the horizontal asymptote.
Okay.
Okay. And then if it ends up going to positive infinity, it's going to come out on the other side at negative infinity. And so we would look at that, but that can't be, because then we would have another x-intercept, and we only found one x-intercept. I'm going to say that in this region, it most likely looks like this. And now that makes me suspect as to what's going on there in the middle. Now, first of all, let's see if this part's right.
Okay.
The only thing we need to see whether that part is right or not is to plug in like -9 for x and make sure that our y value is greater than 2.
Okay.
You see why that would put it there?
Yeah.
Okay. It's going to be hard to be in this one because it would have to cross the x-axis, and we know it doesn't.
Right.
So I'm almost positive that when we put in a x value of -9, we're going to be above 2.
Okay.
Well, what was our function? Our function was this one right here. That's y. And let's see, if we put in -9, we get 2 times -17 times 81 -72 plus 64 in the numerator. And in the denominator, we put -9 for x and -1 for that part. Well, what do we have now? We have, let's see, that number is 73. That number is -34. So we have -34 times +73, all divided by 9.
Okay.
Which is a negative number.
Okay.
Which means it's not in that quadrant.
Okay.
The only other quadrant it could be in is here. which leads me to believe that the curve is going to look like this, and I've made a math error somewhere. I have a 4:30 appointment to go to, but I'm going to be 2 minutes late just so I can graph this thing on Wolfram Alpha, and let's take a look at what it looks like.
Okay.
Let's see how close I am. 2 times x cubed minus 512. 2 times x raised to the 3 minus 512. That whole thing divided by x cubed minus 64x. X cubed minus 64x. Have I showed you Wolfram Alpha before?
No.
It's a great calculator, and I'll show you why. It's going to tell me what I put in there.
Oh.
Your calculator doesn't do that, nor does mine. And that's really hard because some of these functions are very difficult to put in.
Yeah.
It gives you this feedback. That tells me I got it in there right. Okay? And then it gives you a couple of different graphs of it. All right, how does that compare with what I graphed? Well, I'm way off. I must have did some really bad math there. This is one view of it, a close-up view. This is a further out view. Notice the x-axis changes.
Okay.
Okay. This is what's going on between 0 and 8. So I actually am not that far off. I just got it backwards.
Yeah.
Notice that if I take that and make it go down here, turn these, in other words, if I reflect everything over the x-axis, I'm going to have exactly what we're looking at here.
Right.
Wolfram Alpha. So I did something wrong. I'm not sure what, but it was a math error that put me on the wrong side of everything. And I'd have to go back and check my arithmetic to figure it out.
Okay.
But you can see that these are pretty complicated to do.
Yeah.
And I don't know, are you allowed to use a calculator to help you graph?
I think we're going to be allowed to use it on the domain and range just to find like the absolute max.
Well, always do that because if you put it into your calculator just like it was given to you, then at least it will give you a lot of potential. You'll know what the general shape has to be.
Yeah.
In other words, it has to be that over the horizontal asymptote.
Right.
This in between. Notice that we don't ever cross the x-axis. I don't know how I got an x-intercept. There is no x-intercept on this thing. Must have made a mistake in the math, and that's what screwed me up. I came up with an x-intercept of 8. But anyway, I am going to have to run because I do have a 4:30. So I hope I've been helpful.
No, definitely.
Some of these were pretty tough problems.
Yeah.
like this one.
Yeah.
But this Wolfram Alpha, consider that when you're working on work and stuff, because it's really helpful in pinning down what some of these look like, and even just letting you know that you put it in there correctly.
Yeah.
All right, Emma. I will talk to you next time.
Okay, thank you.
You're welcome. Bye-bye.